You've probably heard a million times how models like ChatGPT work, right? But have you ever seen the actual code, the real nuts and bolts? Well, that's exactly what we're going to do today. We're diving straight into the source to build one from the ground up. So, our mission, if you choose to accept it, is to walk through the foundational code of the transformer model. Yep, the one from that legendary paper, Attention is All You Need. We are literally going to build the architecture that changed everything, piece by piece. All right, let's start with the blueprint. What you're looking at is basically the granddaddy of all the huge language models we use every single day. Seriously, this is where it all began. But before we can really appreciate the genius here, we have to understand the massive problem it solved. Think about it. How can a machine understand language if it doesn't know the order of the words? Imagine I give you the words dog, bites, and man. Without order, you have no idea who did what to whom. It's a huge problem, right? And this is exactly what early models just couldn't crack. So how did the transformers solve this? Well, it came down to two honestly revolutionary ideas. These two things are the absolute heart of the model, and we're going to break them down right now. First, something called positional encoding, and then the real star of the show, multi-head attention. Okay, first up, positional encoding. This is such a clever workaround for that word order problem. See, instead of just stamping each word with a number like 1, 2, 3, it gives each position a unique mathematical fingerprint. And it does this using these wave-like sine and cosine functions. What's so cool is that this doesn't just tell the model the order, it also gives it a sense of how far apart words are from each other. Super smart. And here is the actual code that does it. You can see it right there. It's creating that unique signal by hitting the even parts of a word's vector with a sine function and the odd parts with a cosine function. It's a really simple but incredibly powerful trick that gives every single position a signature the model can actually learn. All right, now for the main event, multi-head attention. I mean it, this is the real game changer. If the transformer is an engine, this right here is the combustion chamber. It's the core mechanism that lets the model look at an entire sentence and figure out, for each word, which other words are the most important for understanding its meaning. So what's the multi-head part all about? The best way to picture it is like having a committee of experts. Each head is one expert. So maybe one expert is just looking at grammar, subject-verb stuff. Another expert is totally focused on tracking who's doing what to whom. By having all these different heads looking at the sentence from different angles, all at the same time, the model gets this incredibly rich, deep understanding of the text. Okay, so how does it actually work? That famous scaled dot product attention formula can look pretty scary, I know. But the code really just boils it down to 5 simple steps. First, you score how similar each word is to every other word. Then you scale those scores just to keep the math stable. Then you can optionally mask out words the model isn't supposed to see, like future words in a sentence. After that, a softmax turns all those scores into probabilities, basically attention weights. And finally, you use those weights to create a brand new context-aware version of each word, the context vector. That's it. When you get down to it, it's really just a series of well-organized matrix multiplications. So we've got our core mechanics, right? Positional encoding and multi-head attention. The next stroke of genius was packaging them into these standardized, reusable blocks. Think of them like Legos. This modular design is the secret to why transformers can be scaled up to be so massive. So let's see how these blocks are actually put together. Now, what holds these blocks together? Well, it's this clever little wrapper called a sublayer connection. It's basically the glue. And it does two really simple but totally vital things. It adds the input of a layer to its output. This is called a residual connection, and it's like an information superhighway that bypasses the layer. And then it normalizes everything. This simple combo is what lets us stack these layers super deep without the signal getting lost along the way. Okay, so check this out. Here are the two main Lego bricks we're working with, the encoder layer and the decoder layer. And at first glance, they look pretty similar, don't they? Both have self-attention and a feed-forward network, but there are a couple of key differences. The decoder has to use masked self-attention. That's so it can't cheat by looking ahead at the answer when it's generating text. And it has this extra layer, a cross-attention layer, which is how it looks back at the original input from the encoder. All right, we've got our components. We've got our Lego bricks. Now it's time for the fun part. Let's start stacking and assemble the whole machine. So just how tall do we build this thing? Well, the original paper set the magic number at 6. That's n equals 6. So they built two powerful towers, a stack of 6 encoder layers to really chew on and understand the input, and a stack of 6 decoder layers to generate the output. It's that stacking, that depth, that gives the model all its power. And here it is, the whole shebang. This is the master transformer class in the code. You can think of it as the conductor of the orchestra. It's the thing that pulls every single piece we've talked about together. The word embeddings, the positional encoding, that big encoder tower, the decoder tower, and then the final output piece. This is the complete machine ready to go. Okay, so we've basically built this entire thing from the ground up, right? At least conceptually. But the coolest part is, this isn't just theory. The code we've been looking at is a real working program. So let's see what it takes to actually power this thing on. When you fire up the model, you have to set a few key parameters. These are the main dials you can turn to change the model's size and power. Now, the demo code here uses pretty small values just to make it run fast, but you can see all the important ones. The model's dimensions, how many layers we're stacking, how many attention heads we're using, all of it. For a real production-level model, you just crank these numbers way, way up. And now for the moment of truth, bringing it to life. The code just whips up some dummy data, creates the masks it needs, and then feeds it all into the model. This is called a forward pass, and it's basically like turning the key in the ignition for the first time. The data flows through every single component we just assembled, and if we get an output on the other side that looks right, success. Our machine is working. So, let's just pull all that together for a second. The biggest takeaway here is that these super complex LLMs, they're really just built from simple, modular, and understandable blocks. You've got positional encoding to give the model a sense of order, you've got multi-head attention to let it weigh what's important, and those two things get packaged into encoder and decoder stacks that process and generate information. And when you look under the hood, the entire architecture is just a massive, beautifully organized series of matrix multiplications. That's the magic. So there you have it. We've just walked through the code, the actual blueprint for the AI that has completely defined the last few years. It's an incredible piece of engineering, really. It just leaves you with one big question, right? If this is the blueprint for today's AI, what's the blueprint of tomorrow going to look like?